Welcome to Data Science with EJD. Having done the key things, talking about the key algorithms about unsupervised learning. In the next three videos, I'll be taking some general things related to unsupervised learning before moving on to the next thing. Okay, so in this video, our focus is on unsupervised anomaly detection with isolation forests versus one class support vector machine. Okay, so introduction, since you're talking about anomaly detection, right, we need to know what it is, right? Detecting rare, unusual, or suspicious patterns that differ significantly from expected behavior. That's what anomaly detection is about. Of course, in banking and all that, right? You want to detect fraud, you want to detect things that are uncommon in a situation. Also known as outlier detection or novelty detection, it anomaly detection is critical for fraud detection, e.g., credit card fraud, insurance fraud, fault detection like machinery breakdown, sensor faults, then intrusion detection, e.g., in cyber security attacks. So you would definitely agree with me that these are very important things to detect in a system, right? So talking about types of anomaly detection, we can have supervised anomaly detection. The kind of data you would need in that case is labeled normal plus labeled anomalies. So you have the normal data and the anomalies also labeled, right? By now we know what labeled and unlabeled data are. So example of this will be a classification job involving logistic regression or XGBoost. Then we can have semi-supervised anomaly detection. In this case, you need labeled normal data only without labeled anomaly data. So what the system does is to detect whatever data there is, though unlabeled, whatever anomaly there is in the system, despite the fact that it is unlabeled, right? An example of this will be the kind of thing we are considering in this situation. So we're talking about novelty detection using one class support vector machine or isolation forest. So and you can have unsupervised anomaly detection. Here, there are no labels at all, no labeled normal data, no labeled anomalous data. So no labels at all. You detect outliers, assuming they are rare and different. And here you can use clustering or isolation forest for that. So our focus is unsupervised because labeled anomalies are often scarce. So because you don't even know there's going to be something wrong in the well, you expect that things might go wrong, right? But you don't really know how things will go wrong sometimes, right? So that's why it's difficult to come across labeled anomalies. So the algorithm overview in this situation will be as follows. Um, for isolation forest, the core idea is that you have anomalies that are few and different. So in that case, they are easy to isolate. So in that case, you can use isolation forest. Then you can then randomly pick a feature and split point. That is, you build some kind of trees. When you hear forest, we've talked about decision trees, random forest. Now we're talking about isolation forest. So it's like you are picking out an unusual tree. So anomalies get isolated quicker, shorter average path length. So the strengths of isolation forests lie in the fact that it scales well to high dimensions. It is fast. It can be trained very fast, and it has fast training and prediction, and it is less sensitive to parameter tuning. Then when we go to one class support vector machine, the core idea is to find a smooth boundary that encloses the majority of data. So any data that falls out of that, points lying outside this boundary are outliers. So they are the anomalous situations. They are the anomalies you're trying to detect. Then one class support vector machine uses kernel trick, e.g., radial base function to model nonlinear shapes. All right. So the strengths of one class SVM include the following: effective. It is effective for well separated clusters. So if the clusters are well separated, you can use one support. You can use one class SVM. Then it is good when the normal class has clear boundaries, and it is more sensitive to parameter tuning like nu and gamma. All right. So let's look at some use cases, just like what we've hinted from the beginning. So you can have credit, you can apply a detection of anomalies in credit card fraud. And in using isolation forest, it will be good at high dimensional transaction features. One class support vector machine would be good for smaller samples. So if you have smaller samples, you can go for one class SVM. If you have larger samples, you go for isolation forest. Talking about machine fault detection, isolation forest handles multi-sensor data well, while one class support vector machine works for clear normal behavior. Then for application, it works for network intrusion. Talking about network intrusion, isolation forest is fast on big logs, and one class support vector machine is good for well-behaved normal traffic. So comparison with supervised anomaly detection. So um, if you talk about labeled anomalies, if you when labels anomalies are needed, you cannot use unsupervised anomaly detection. So you cannot use isolation forest and one class support vector machine. But once you have labeled data, you can do support. You can do supervised anomaly detection using XGBoost and logistic regression, for instance. Then if you want to be able to detect unseen anomalies, unsupervised learning is good. And then supervised learning would not always work here. If you are concerned about performance with enough labels, unsupervised learning is not that good, while supervised learning is excellent for that. Then if you want to know how common these things are, um, unsupervised learning is good for new domains or scarce labels, while supervised learning is good for mature domains and well labeled data. So the key point here is that when labeled anomalies are available in sufficient numbers, supervised detection is usually more accurate. So if there's a very common occurrence of a certain anomaly in a system, supervised learning can work good in that situation. Okay, so let's do a systematic Python implementation of this whole of these two algorithms, isolation forest and one class support vector machine. Below is a complete, clear, reproducible pipeline you can adapt for any dataset, synthetic or real. So first of all, we import the libraries, right? Okay, so here you have now I've run all the codes because it can be quite slow. So I don't want to record I don't want to record it while it's running as like I've always done, because here we are dealing with a lot of data, and it can take like up to much as 3 minutes to run some codes here. So I ran everything ahead of time, so that I don't have to waste time waiting for it to run. So import the libraries. You need NumPy, you need Pandas, you need Matplotlib, of course, because of visualization. Then for the isolation forest model, you get it from scikit-learn ensemble. For one class SVM, you get it from scikit-learn SVM. Then dataset. Anytime you see make blobs, it means that's a kind of synthetic data, and it's very good for for learning things like clustering and all that. So for the metrics here, of course, we are going to use classification reports and confusion matrix. So, I mean, make sure you run that. I've run it. That's why number one is showing here. Then create example data. So to create example data, now what we did is X normal. So from the make blobs, now we're making 300 samples. Centers is one, clustered is 0.6, random state is 42 for reproducibility. Then create outliers. So for the outliers, we have np.random.seed 42 for reproducibility still. So the outliers are now, so the low -6, high is 6, size is 20 by 2. Then we combine the normal data and the outlier data. Of course, this is made up data, right? So by the time we combine it together in line now, we have X is NP NumPy. This is why we needed NumPy. NumPy.v stack. So you're stacking it vertically. So you have X normal, X outliers like that. And then for the true labels, 0 is normal and Y is anomaly. So Y true now is NP dot horizontal stack now. You have NP zeros, X normal shape 0, NP ones, X outlier dot shape 0, and then you run that. At the end of the day, we end up getting a data shape of 320 by 2. 320 by 2. Then, of course, for the X outliers now, see the kind of things you have here. These are the X outliers. And then for the Y true, you have all of these things like that. You have the data in this format. So to fit isolation forest, of course, once you fit it, it's done. And you don't necessarily want to see anything here. And then you also fit one class SVM, because those are the two things you're comparing. And then you can then evaluate the performance of each of the models, isolation forest and one class SVM. Of course, you have their metrics here, the precision, recall, F1 score, and support, right? So you have, overall, if you just look around, you have 0. I mean, the least you have here is 80%. So that shows isolation forest is so good. But then when you come to one class support vector machine, I mean, it's good also, but then you have things as low as 50% in some situations for recall and all that. So based on this, we can have a hint that isolation forest is better than one class support vector machine. Of course, for obvious reasons, because you discover that generally speaking, right, when you compare decision trees and random forest, because a forest is an aggregation of trees, right? So you expect to get better results, at the end of the day. So to visualize the data, right, we want to see, so you see isolation forest right here, and then you see one class SVM. Well, from the data, so you can see that the normal data is properly distinguished. It's easier to detect the anomalies using isolation forest. For one class SVM, you can still have some anomalies right with together with clustered with the normal data. So that might just be one reason. So the red dots actually show you the anomalies, while the blue ones are the normal data, right? So of course, based on the metrics we saw, we can also see the isolation forest works good. It's more preferable to one class SVM because the anomalies are easily detectable, you know, in that situation. So how to use if you now want to use this with a real data set, like for credit card fraud, for instance. So in this case, of course, we are just doing this whole thing again, which is not necessary, right? Since we've uploaded all these things up there, we don't have to do this, except for maybe we now need Seaborn and we now need to pre-process and do some decomposition like this as means of visualization. So that has been run also. Now this is number 9. Now this is jumping to 17 because after running, you see, this is 9. Uh, this is uh, that's 9 already, right? Okay, that what you had here was 10, and then you went to 11 and so on. But after doing everything, I came back to do this. That's why the numbering is like this. So I came back to do this later because I wanted to really visualize this. This credit card data set is actually on kaggle.com. So you can find it on kaggle.com. It's one of the data set that are used for unsupervised learning for things like this. So this is what the data looks like. You have time, you have all this V1, V2, V3. So like some credit card transactions, the amount of transaction and all of these things. So that's what you have. So and it's a large data set having 284,807 rows. That's 284,807 data points with 31 columns. That's 31 features right there. So here now we want to so if you look at the class, right? If you look at the class, so the class counts. So for zero, that zero is the normal data. So you have 284,315 normal transactions, while 492 are anomalies, right? So from this data set. So the next thing we want to do is to scale the features, like that's on pre-processing. So you can drop time column for simplicity, because I mean we don't really need time for. Well, of course, if you are doing like a forensic thing or something, you may want to know when when a wrong transaction was done, so that can help to trace it to where the fraud is coming from, possibly. So drop time column for simplicity. So you have X is df dot drop time and class. You drop all this. Then Y is df class. Zero is number, one is fraud, just like you've seen up there. Then you scale. The scaling is to normalize the data. We've done that quite a number of times. Then you fit to isolation forest, just like we did for that blob for the synthetic data. Then you fit to one class SVM again, and then you evaluate. Generally speaking, you see that SVM seems, if you compare point for point, right? So precision 1 1 good. Then for precision is 26%, whereas this one is just 9%. Recall 30% here, 23 here. So overall, you still see that isolation forest works better than one class support vector machine generally. So even for real data now that we got from Cargo. So if you can also want to visualize the PCA. So here, since the data has 30 plus features, we can project it to 2 dimension with PCA and color by ground truth and predicted anomaly labels. Now, you see, the trouble is once you have more than 2 or 3 dimensional data set, PCA Things like PCA and TSNE, they come in handy, or even UMAP, they come in handy to help you, visualize the data in 2 or 3 dimensions without losing so much information, right? So, and that's why here this has been run already. So we want to reduce the whole, 30 plus features, right? I mean, what we have here tells us we have what's that now? Okay, yeah. 280, 284,807 rows and 31 columns. So 31 features altogether. So that's difficult to represent except to take them in pairs. But then with PCA, we can actually do a two-dimensional representation of these things without having to lose so much data there. So, using this, if you run this together, PCA uh, ready, but then you now need to plot that. So we plot all this. So we do for the ground truth, that's the original thing. Then we go for the isolation forest prediction and one class SVM prediction. So you can see again, we are here. So this is the original, the ground truth, right? When nothing has been done, so to speak. Then when it comes to isolation forest prediction, so you can see that, the I mean, at least if you compare with one class support vector machine prediction, so you can see that the anomalies really stand out. Of course, there's still a kind of mixture, but it stand out compared to what you have for one class support vector machine. And the metrics also tell us the reality. So that's the plot in that situation. So what the plot show us, the left one, right? This left one is the true normal versus fraud in 2D PCA space. And here you have the middle, which is isolation forest detected anomalies. They are a bit more distinguished. And then here, one class support vector. So you still have a whole, in fact, you still have normal stuff coming all the way into the outlier there. So that tells you that the SVM is not doing as good a job as isolation forest is doing. Okay. So, red points indicate anomalies, like we said, that's fraud as labeled or predicted. You can visually inspect how well each unsupervised method isolates the rare fraud transactions. So, like we said already, isolation forest seems to be doing a better job. So, practical tips, isolation forest. So, the default to contamination equals estimated anomaly rate. So, we can try this out. I mean, we can do this. So, that's the default. Then, one class SVM, you can tune new, which is anomaly proportion. That's in training the SVM now. Here you have you have nu, you have gamma. So you can change the value of the nu, you can tweak that to see what happens like that. All right. So we have all that going on there. So you can scale features if needed, especially for one class SVM. I think we did that actually. Then you can use ROC or AUC, ROC, AUC or precision recall if labels are available. So if you have labels, you can do this. Then you can try more sophisticated dimensionality reduction like TSNE or UMAP, like I said, for better visualization. So if you are doing it, of course, if the data is not a linear data, if the data has some non-linearity in it, so it's better to visualize using TSNA or UMAP instead of PCA. So because PCA is basically for linear data dimensionality reduction, being one of the algorithms under supervised learning. So for serious fraud detection, you can combine this with domain rules and supervised learning. So in summary, isolation forest, it's strong when it comes to scalability. It is robust, it is fast. One class SVM is flexible, non-linear with non-linear. It has flexible non-linear boundaries actually. Then the weakness for isolation forest is that it may struggle with very subtle anomalies, and one class SVM is sensitive to large noisy data, so it can easily detect fraud as normal transaction, right? Then for data, isolation forest can work with high-dimensional big data, while one class SVM only works with small, medium data. For the tuning for isolation forest, you need the contamination. For one class SVM, you need nu and gamma, right? Did we see contamination in isolation forest the other time? Isolation forest. Where is that now? Yeah, yeah, we have the contamination there. So the contamination just looks like what nu does for one class SVM. So you can change these values. You can keep tuning that to see to get the results you desire. So for the next steps, right? If you want to take this further, right, you can try it on real fraud or false data. You can compare with supervised models like logistic regression, XGBoost, if you can get labels. And you can combine with feature engineering like statistical summaries, time windows, and domain knowledge. And with this, we come to the end of this very interesting video talking about detection of anomalies, unsupervised anomaly detection with isolation forest versus one class SVM. If you let me know how helpful this video is for you. If you have not subscribed already, please go ahead and subscribe. And for those who have subscribed, thank you very much for that. And don't forget to hit the notification bell so you can always get alerted each time a new video is released. You can become a member of the channel. Right now we are going for 1,000. I have just less than 10 subscribers to hit 1,000. So you want to make that happen. Thank you for that already. Yeah. So don't forget you can download my code sheets from Google Drive. Just check the description box or either on Facebook or on YouTube, and then you get all the code sheets and data sets download, and then you can follow step by step as I go. If you see a number, tweak it, see how it changes the system, and that way you can actually learn for real. So be sure to like and share also so that more people can have access to this video content I have going on here till I come your way again. Keep doing data right. Bye.